the first thing that we're going to do today is talk about sinusoidal signals. So I'm going to draw, and I'm going to do my best, although this usually comes out pretty poorly. I'm going to do my best to draw a picture of a sinusoidal waveform. And just for the sake of argument, let's call this waveform a voltage. All right, so we could characterize this sinusoidal waveform with the following function. V of t is equal to Vm cosine omega t plus theta v. And we're going to talk about what all of these constituent parts of the sinusoid mean by inspecting our graphical representation. Okay. So our first bit, Vm, is the amplitude or maximum value of our sinusoidal function, V of t. So it represents the difference between the peak value and the horizontal axis. And technically we consider Vm to be the maximum value, but it could also be representing the distance from the most negative peak to the horizontal axis as well, simply the magnitude of that size, okay? So Vm tells us how large our sinusoidal signal is. Omega is the angular frequency of V of t measured in radians per second. Okay. Now we can't look at our graph and immediately develop a relationship for omega. We have to look at a couple of other things very quickly here. Okay. So what we're going to look at is what's called the period of the function. Okay. So I am arbitrarily choosing to define the period, which will be capital T, as the amount of time that occurs between successive negative peaks. We could define it to be the time that occurs between successive positive peaks. We could define it to be the time that occurs between zero crossings that are increasing, the time that occurs between zero crossings that are decreasing. Doesn't particularly matter how we define it for any periodic signal. Wherever we start, whenever we hit that exact same value again, we have exactly one period, okay? Well, So t is the period of v of t. F is the linear frequency of v of t, where f is simply 1 over capital T. You guys actually first got introduced to, at least here at Louisiana Tech, in your engineering 121 class, okay? So if T represents how long it takes for one cycle to occur, F tells you how many cycles per second occur, because there's that inverse relationship between the two of them. Finally, circling back around, we can define our angular frequency mathematically as omega is equal to 2 pi f, because it's the total amount of angle covered in a cycle. So that's 2 pi or 360 degrees times 1 cycle per second, giving us radians per second. Or alternatively, we could write this as 2 pi over the period. And so now that we've developed these relationships, we can easily see what effect the shape of the graph will have on omega, right? So if the peaks are scrunched together, we have a large omega. If the peaks are spread out, we have a small omega. Okay. T in our equation simply represents time, so I'm not going to talk about that too much. Theta v is a very important thing that you may not have been introduced yet. So theta v is the phase angle of v of t. And essentially what it does is it determines the function's value at t is equal to 0, right? So for a standard cosine function, what should its value be at t is equal to 0? So if there were no phase angle whatsoever, 1. So what this phase angle does is it sets the value at t is equal to 0 to something that isn't 1, or I guess 1 would represent a phase angle of 0. So another way to think about this is the phase angle represents a time shift away from whatever its normal value at 0 is. So for instance, in this graph, we see that our cosine function reaches its peak value at some point in time later than t is equal to 0. That would be indicative of a right time shift, which means so that the peak is occurring at a later point in time, which means that we would have a negative phase angle. If instead the peak value occurred before t is equal to 0, that would be a left time shift, which would be indicative of a positive phase angle, because the peak value is occurring earlier in time than t is equal to 0. So I'm going to write all that down so you don't have to just remember it. So positive phase angles. So if theta v is greater than 0, causes shifts to the left by a time delta t is equal to theta v over omega. And when theta v is less than 0, this causes shifts to the right by that same expression. So these three things, amplitude, angular frequency, and phase angle, define a sinusoidal signal. Now, oftentimes, we will be asked to compare sinusoidal signals. And there are a few very specific rules that we need to follow in order to do this. Okay. Our first rule is that, actually, I'm going to call this A. Rule A. Our first rule is that all functions must be expressed exclusively as sine functions or cosine functions. So let's say that we had a signal VA of t that was 8 cosine 5t plus 10 degrees volts. And let's say that we had a second signal, VB of t, that was equal to 3 sine 5t plus 45 degrees volts. Only way that I can do a valid comparison between these two signals is to either change VB of t to a cosine function or change VA of t into a sine function, okay? Now, I'm going to scroll back up here so that we can look at our original graph. Hopefully, we all know that sinusoidal functions, both cosines and sines, look identically the same. It's just one signal is more advanced in time than the other, right? So we're now going to introduce a couple of trig identities that will let us convert back and forth between sine functions and cosine functions. So these trig identities, which I'm going to call identity number 1 and 2, are cosine of omega t is equal to sine of omega t plus 90 degrees. And alternatively, we could say that sine omega t is equal to cosine omega t minus 90 degrees. So let's say that we wanted to convert signal VB into a cosine function. All we need to do then to convert from sine to cosine is subtract 90 degrees from the angle, which means 3 sine 5t plus 45 degrees looks like 3 cosine 5t minus 45 degree volts. And now both of our signals are expressed as cosine functions, and we could do some sort of comparison operation. Our second rule, so I'm going to call this rule B, is that all functions must be expressed with positive amplitudes. So if I had a third signal, let's call it VC of t was equal to -5 cosine 5t minus 110 degrees volts, how would I convert that to having a positive amplitude? So we would simply treat it as if it were shifted either to the left or to the right by 180 degrees. So if let's look at some things here real quick. Let's do it in red. So theta v by itself corresponds with this positive peak, right? And when we hit our second positive peak over here, this would be theta v minus 360 degrees because we're time shifted to the right by one full cycle, okay? Well, right here, where we have our negative peak, is a time shift of 180 degrees. So to change the sign on a sinusoidal signal requires a phase shift of 180 degrees, but we can say that it's plus or minus because it really doesn't matter which direction we go, right? So over here, this would be theta v plus 180 degrees. Either instance gets us to the negative value. So from these relationships that we just explored graphically, we can write two more trig identities. Negative cosine omega t is simply positive cosine omega t plus or minus 180 degrees. And negative sine omega t is simply sine omega t plus or minus 180 degrees. Our third and final rule for comparing sinusoids is that all functions must have the same frequency. I'm going to put here omega or, so they all have to have the same angular frequency or they all have to have the same linear frequency. There is no trig identity to fix this, okay? If it is operating at a different frequency, we simply cannot draw a valid comparison. There's no manipulation that we can do to make a sinusoidal function that's, say, oscillating at 8 radians per second look like a sinusoidal function that's oscillating at 5 radians per second. So those are our three rules. And in the course of developing those rules, we've also developed 4 trig identities. Let's talk about one comparison that is done frequently in the field of electrical engineering, which is called determining whether a function is leading or lagging. Okay. So I am going to, again, attempt to draw a series of sinusoids. I'm going to try to draw the three that we have described here. So this is V of t, so let's see. Our first one was VA of t, where we had a cosine of positive 10 degrees. All right. We did that in blue. So a positive 10-degree phase shift would mean that we would hit our peak value just prior to t is equal to 0, because a positive phase angle means that we are shifting to the left, right? So actually, let me scooch this over a smidge. So our blue curve is supposed to represent VA of t, 8 cosine 5t plus 10 degrees. Then I think we did red, so 3 angle negative 45. A 45-degree phase shift would mean that we've shifted to the right by some amount. So again, me purely just eyeballing things here. Trying to figure out what to do with my scale here to make things as correct as possible. I think this will be about right. Again, apologize for my poor drawing skills. Something about like this. And finally, VC of t we did in green. So that was, oh, actually, we didn't ever actually convert it. So let's do that briefly here. So I'm going to arbitrarily add 180 degrees here just so that I get an angle between negative 180 and positive 180. So that would look like 5 cosine 5t. And if I add 180 to negative 110, I get plus 70 degrees volts, like so. And so we're going to have VC of t is equal to 5 cosine 5t plus 70 degrees, which should look something like this. All right, so if we wanted to determine which signal is leading or lagging, effectively, all that we are doing is deciding which signal hits its peak amplitude first. So for example, based on this graph, we could easily see that VC of t leads VA of t. VC of t leads VB of t. And that VA of t, excuse me, VC of t. No, I had it right. Sorry, confusing myself what I'm looking at here. VA of t leads VB of t. I'm making all of these inferences based purely on the fact that VB of t hits its peak value at a later point in time than the other two signals, right? So VA hits its peak first here. I'm going to call this TA. Sorry, actually that's TC. A hits its peak here. Peak here. TC is at an earlier point in time than TA and an earlier point in time than TB, which is why I'm saying that VC leads VA and VB. TA occurs at an earlier point in time than TB. That's why I'm saying VA leads VB. We could also look at things the other way around, okay? So we could say that VB of t lags VA of t because its peak value occurs later. We could say that VB of t lags V of t. And we could say that VA of t lags V of t. This is the exact same comparison as we had a moment ago, just looking at it from the opposite perspective. So we're looking for whichever one occurs latest is lagging the things that occurred earlier. Okay. Now, I personally have difficulty looking at this type of graph and determining these relationships. Okay. So what I'm going to introduce to you, this is not remotely anything that I've invented by any stretch of the imagination, but what I'm going to introduce to you is a different way of looking at these graphs, which is called a phase diagram. Okay. So in a phase diagram, we have a plot. And it is simply a plot of angles, okay? So the positive horizontal axis corresponds to 0 degrees. The positive vertical axis corresponds to 90. The negative horizontal corresponds to plus or minus 180 degrees. and the negative vertical corresponds to negative 90. And so what a phase diagram is a snapshot in time of these signals. So instead of looking at them as a function of time, we evaluate them at one very specific point in time. And I'm going to use t is equal to 0 as our specific point in time. So at t is equal to 0, we have an amplitude of 8 and an angle of 10 degrees. So that would be something, oops, this should be in blue. Something like this. And for VB, we have an amplitude of 3 and an angle of negative 45 degrees. And then finally in green, we would have VC, which would be 5 with an amplitude of 5, angle positive 70. So that would be something like this. I'm just going to label these VC, VA, and VB of t. Effectively, what we're looking at here is any angle its phase angle is more positive than the others is leading, and any that's more negative than the others is lagging. So for example, if we wanted to see by how much VA lags VC, we would start measuring. I'm going to do this in purple because I haven't used that yet. Start measuring from VC. Actually, I'm going to write this down so that it's clear what we're doing. How much does the A of t lag Okay, so we're going to start measuring from VC because that's our reference. And we're going to measure our angle in a clockwise fashion, like so. And we're going to stop when we hit VC, or excuse me, VA. So in this case, this is simply 70 degrees minus 10 degrees is equal to 60 degrees. Anytime we're measuring in the clockwise direction, we're measuring lagging. Anytime that we measure in the counterclockwise direction, we'll measure leading. So let's do something there. Let's say how much does the A of t lead the B of t? This in pink because we haven't used pink yet. And all I'm going to do here is really just extend this thing down just so I'm not writing over things. The angle hasn't changed at all, right? So since we're comparing to VB, we start measuring at VB, and we're going to measure in a counterclockwise fashion, CCW, for leading. And we can see that this is going to be simply 45 degrees plus 10 degrees is 55 degrees. So we're just finding the difference of the two angles. That's all we're doing when we're measuring leading or lagging. Okay. Now, I want to tell you guys something about your homework set, okay? The method that I have described here is 100% correct. But if you follow this method in web work, there is a distinct possibility that it is going to tell you that your answer is wrong. Let me explain to you why, okay? Web work cannot differentiate between 0 degrees and 360 degrees and negative 360 degrees. It doesn't know that those are all equivalent angles. Or you could say that it doesn't know that, I don't know, 45 and 405 are the same thing, stuff like that, okay? So if you follow this methodology to do your homework problems on this, and it doesn't give you, it doesn't tell you that your answer is correct, try adding 360 degrees to the angle that you get. If that isn't correct, try subtracting 360 degrees from your original angle. One of those three things, either direct computation, add 360, or minus 360, will be absolutely correct, and web work will accept it. But because it can't tell the difference between equivalent angles, depending on how the problem was coded and the numbers that you get, it tends to freak out. Okay, so I'm just telling you very explicitly why web work isn't going to like some of the stuff some of you are doing and how to fix it. You are doing it correctly if you're following this methodology. If web work tells you otherwise, add 360 or subtract 360. One of those will be the correct answer. And they all represent the exact same angle. So you're not doing anything or fudging anything there. Okay. All right, so this is leading and lagging. What I'm about to do now is give you a list of useful trig identities for manipulating sinusoids, 4 of which we've already developed, and a few more we are going to utilize in this class. All right, so numbers 1, 2, 3, and 4, we've already talked about. That was cosine of omega t is equal to sine omega t plus 90 degrees. And the opposite, sine of omega t, is equal to cosine of omega t minus 90 degrees. Then we had the identities that we developed for getting rid of negative magnitudes. So that was negative cosine omega t is equal to cosine omega t plus or minus 180 degrees. And negative sine omega t is equal to positive sine omega t plus or minus 180 degrees. The next 4 that I'm going to give you, you should have learned in your trig classes. And we are going to use them to effectively break up sine functions into their constituent parts, okay? So our first one is going to be sine alpha plus beta is equal to sine alpha cosine beta plus cosine alpha sine beta. Second is cosine alpha plus beta is equal to cosine alpha cosine beta minus sine alpha sine beta. And that negative sign there in the middle is correct. And we'll have sine alpha minus beta is equal to sine alpha cosine beta minus cosine alpha sine beta. And Lastly, cosine alpha minus beta is equal to cosine alpha cosine beta plus sine alpha sine beta. Okay. So these last four trig identities here are used extensively in the analysis of steady state sinusoidal circuits in the time domain. Okay. We're going to analyze a circuit in just a few moments that satisfies those constraints. Okay. And then we're going to talk about a different way to approach it. These next two identities are very fundamental to analysis that we're going to be doing later on. Okay. So number 9 here, this is what's called Euler's identity. And it says that cosine omega t plus some phase angle phi plus j sine omega t plus some phase angle phi is equal to e to the j omega t plus some phase angle. This is nothing more than converting a rectangular form complex number into a polar form complex number, which we developed those relationships in our last class. So this is just a fancy way of representing that. Our last identity, which we're not going to use until we actually hit power-based relationships, is cosine angle 1 times cosine angle 2 is equal to 1/2 cosine angle 1 minus angle 2 plus 1/2 cosine angle 1 plus angle 2. It's going to be about a week and a half until we wind up using number 10 here. All right. So we have spent 45 minutes doing background information to bring you guys up to speed on what I'm about to do. Okay. Looks like people are still writing stuff down. Okay, let's move along here. I'm going to call this section forced response due to sinusoidal inputs. And I'm going to put in parentheses here, time domain. So we touched very briefly on the concept of forced responses when we were covering transient analysis. What a forced response meant was that we had some sort of forcing function, so a voltage source or a current source, that was causing a signal, maybe an inductor current or a capacitor voltage, to have some specific value. Okay. So for example, if we had the following circuit where we have a voltage source in series with a resistor, which is in turn in series with an inductor, and our goal was to determine the response of this system, defined in this case as the current flowing around this loop, which our response will always just be a voltage or current signal, what would our response I be? Vs over R. So I really like the way that you phrased your answer there. Mr. Rayford said that since it's a DC circuit, our current I would just be Vs over R. So what you have unknowingly done is exactly what I'm talking about here, okay? In a DC circuit, we expect to get a DC response, right? So if we have a constant in time forcing function, we expect to get a constant in time response to that, right? Not only is our current here, I, a DC quantity, the voltage drop over our resistor is a DC quantity, the voltage drop over our inductor is a DC quantity as well. So all of our signals are DC signals because our input or our forcing function is a DC source. So based on that logic, if I had the following circuit where I have a time varying voltage source connected to a resistor and an inductor, I'm going to call this I of t, inductor is L. I would expect that my current I of t will have the same form as my forcing function, right? So if Vs of t is equal to Vm cosine omega t plus theta v, we should expect I of t to be of the form Im cosine omega t plus theta I, right? So if we put a sinusoidal forcing function in, we should expect to get a sinusoidal response where our magnitudes might be different, our phase angles might be different, but our omega has to be the same, because if we excite the function at one particular angular frequency, all of our signals should occur at that exact same angular frequency. Okay. So what we are going to do is analyze this circuit in the time domain. And purely to make our math a little easier to follow here, I'm going to explicitly start with theta v is equal to 0 degrees. Okay. What we're going to develop is applicable for any value of theta v, but it's just going to be cumbersome in the math if we make that angle non-zero for right now. Okay. So we are going to symbolically analyze this circuit and develop a relationship for I of t. This is going to be, I would say, difficult. Okay. Seems like it should be pretty straightforward, but I believe it to be reasonably difficult. So what I'm going to do here is I am going to call the voltage drop across my resistor VR of t, and the voltage drop across my inductor VL of t. And I am going to apply Kirchhoff's voltage law And doing so, we can find that Vs of t is equal to Vr of t plus VL of t. Which is the same as simply R times I of t plus L di by dt. So I'm going to do this in blue because we're probably going to ignore this part in a minute, but I'm just simply going to substitute in my value for I of t here, right? So we've made an assumption here, which seems pretty valid, that I of t will be of the form that I've described above. So we're simply going to substitute that into our differential equation here. So that means that we're going to have Vs of t is equal to R times Im cosine omega t plus theta I plus L times the derivative of Im cosine omega t plus theta I, which is R times Im cosine omega t plus theta I plus omega L Im sine omega t plus theta I. And just to be clear here, the derivative of cosine is negative sine, right? All right, so I'm going to change that positive sign I had to negative to account for the fact that when I do the derivative, I should get a negative sign there. All right, so what I have here is an expression that is effectively the sum of two sinusoids. And my goal here is to express Im as a single sinusoid, okay? So I'm going to have to do some manipulation here. I'm going to use some of the trig identities that we developed, or that I introduced previously. We didn't develop these. And so what I'm going to do is I'm going to split my cosine omega t plus theta I function into two sinusoids using trig identity number 6. And I'm going to split my sine omega t plus theta I function into two sinusoids using trig identity number 5. So this is going to look like R times Im. We use trig identity number 6, where we're treating omega t as alpha. That's going to look like cosine omega t times cosine theta I minus R Im sine omega t sine theta I. That's literally just splitting the first one. And then I'm going to subtract from that omega L IM. And now I'm applying trig identity number 5. I'm going to have sine alpha, so sine omega t, times cosine of beta. So that's cosine beta I plus omega L IM cosine alpha, cosine omega t times sine of beta, so that's sine beta I. All right. So all I'm going to do here, just really quickly, is get rid of those brackets by distributing that negative sign in the second line, okay? So I can get rid of these brackets by just putting a negative sign right there. And now what I am going to do is I'm going to lump together things, okay? So I have R times IM times cosine beta I plus, let's see, RIM cosine theta I minus omega LIM sine theta I times cosine omega t. And then I have, I believe, minus RM IM sine omega I sine theta I plus omega L IM cosine theta I times sine omega t. Are we all with me algebraically so far? Have I made any mistakes or anything here? Yeah, sorry, there, yeah, RM is not a thing, so it should just be R. Thank you. R times I. Yeah. Okay. So what I'm going to do here to make our life arguably a little easier is I'm going to call IM cosine theta I A1, and I'm going to call negative IM sine theta I A2. Just doing a simple substitution here so that I don't have to carry through too much stuff. And so what this should give me is Vs of t is equal to, so let's see. So I have R times Im, so that's A1R plus A2 omega L cosine omega t plus A2R minus A1 omega L sine omega t. All right, I'm going to leave my right-hand side alone here. I'm going to now express Vs of t in its cosine function form, right? We defined it way, way back up here as Vm cosine omega t plus 0 degrees. So I'm simply going to erase this Vs of t and put in Vm cosine. Now, it may not look like it here, but we have a system of equations. So let me explain exactly what I mean by that, okay? What we have on the left-hand side of the equal sign has to equal what we have on the right-hand side of the equal sign. So the coefficient of the cosine function on the left-hand side is Vm has to equal to the coefficient of the cosine function on the right-hand side, which is A1R plus A2 omega L. The coefficient of the sine portion on the left-hand side, which is 0, has to equal the coefficient of the sine portion on the right-hand side of the equal sign, which is A1R minus, A2R minus A1 omega L. Sorry, I made this L look like a subscript when it shouldn't have been. If I solve these two equations, what I get is that A1 is equal to R times Vm divided by R squared plus omega squared L squared, and A2 is equal to omega L Vm over that same denominator, R squared plus omega squared L squared. Our goal here, now that we know what A1 and A2 are, is to figure out a way to convert our current, which, just to be clear here, let's see, to convert our current back into a single sinusoid where its amplitude is expressed in terms, excuse me, of our component values, and its phase angle is also expressed in terms of our component values. So we know that Im cosine theta I is equal R Vm over r squared plus omega squared L squared. And we know that Im sine theta I is equal to negative omega L Vm over r squared plus omega squared L squared, right? So I'm going to take these relationships and I'm going to play around with things here. For instance, Im cosine theta I squared, I have enough information to figure out what that is, plus Im sine theta I squared. I have enough information to know what that is. Well, this has to be equal to Im squared cosine squared theta I plus sine squared theta I. Well, what's cosine squared plus sine squared? 1. That means I can figure out what my magnitude is purely in terms of my components now, right? So Im, actually, let's do it squared and then take the square root so the math will be easier for us. Im cosine theta I squared just looks like r squared Vm squared over r squared plus omega squared L squared quantity squared positive Im sine squared is just going to be omega squared L squared Vm squared over r squared plus omega squared L squared squared. And I can lump things together here. Oops, that's not what I wanted. So I have a common factor of Vm squared. This is going to be multiplied by r squared plus omega squared L squared divided by r squared plus omega squared L squared quantity squared, giving me the magnitude squared is Vm squared over r squared plus omega squared L squared. Or finally here, the magnitude of our current, Im, is Vm over the square root of r squared plus omega squared L squared. So we know what the magnitude of our current is purely in terms of our component values effectively. To get our phase angle, we know that tangent of theta I is equal to the sine of theta I over the cosine of theta I, right? Tangent is sine over cosine. Does it change anything at all if I multiply both of those trig functions by Im? No, we'll just cancel each other out, right? So what this is going to give us is negative omega L Vm over r squared plus omega squared L squared divided by r times Vm over r squared plus omega squared L squared, which is simply negative omega L over R. And from this, theta I is the inverse tangent of negative omega L over R. And from this, I of t is Vm over the square root of r squared plus omega squared L squared times the cosine of omega t plus the inverse tangent of negative omega L. So we've solved it. Took us half an hour for a circuit containing literally two components. Now, let's take a moment here to throw some numbers in and make sure that we're not absolutely insane, all right? So let's circle back to our original example. Let's say that R is 10 ohms, L is 1 Henry, Vm is 8 volts, and omega is 2 radians per second, okay? So using these numbers, we have Vm, sorry, I didn't remember what I wrote down, 8 over the square root of r squared, so that's 10 squared plus omega squared, so that's 2 squared times L squared. I get 0.784 cosine omega t, so let's call this 2t, and then I have the inverse tangent of omega, which is 2, times L, which is 1, over R, which was 10. I'm going to multiply that by 180 over pi to get it in degrees. So I didn't use inverse tangent, sorry. Inverse tangent, negative 2 times 1 over 10. Negative 11.5 310. What I got. Amps. So this is what our response IS of t came out to be. Give me just a moment here to do a quick thing to check my work. All right, so we did a solid half an hour's worth of work to get this result for a circuit that had two elements in a source set. So working a problem like this in the time domain, while possible, because we literally just did it, isn't really the best use of our time, okay? Now, some of you, none of you today, but in the past, some of you asked after we did all this, well, if we're gonna do all this stuff in the time domain, why did we bother learning all that complex number junk in our last class? So what I would like for you guys to do is, let's see if we can go to an intermediate step here that would require a lot less work. It would require us. It doesn't look like. Okay, so sorry. Different way to approach this because I work this problem differently than how I've done it before. Okay, so what we are going to do now, have to rewire my brain to think about this slightly differently, is we're going to approach this problem from a very different perspective, okay? Instead of using these time domain relationships, which took us a very, very long time to analyze this, we're actually going to use complex numbers. And so let me explain why we're going to give that a go, okay? So what are the three things that define a sinusoidal function? We talked about them at the beginning of class. Amplitude, frequency, phase angle. Those three things also define complex numbers. Amplitude, frequency, and phase angle, or at least an exponential form complex number, okay? So we have, just to be clear here, our amplitude IM, our frequency omega, and our phase angle I. So I would argue that we could write I as a complex number as IM e to the j omega t plus theta I, and it would contain the exact same amount of information, right? It contains an amplitude, a frequency, and a phase angle. All right. So if we had, actually, I want to show you guys something just really quick using Euler's identity. The real part of this complex number I is actually IM cosine omega t plus theta I. So the real part of the complex number that we are going to use is actually the time domain signal we just messed around with. Okay. So we're going to rework this problem. We have ES of t here. We have R is equal to 10 ohms here. equal to 1 Henry here. Here's I of t. We're going to rework it using complex numbers. So let's say that Vs of t is Vm e to the j omega t. Again, we're saying our phase angle is 0. And our expectation, Is of t, is equal to Im e to the j omega t plus theta I. We know that Vm is 8 volts, and we know that omega was 2 radians per second. That's what we used earlier. I'm going to call my voltage drops the same as I did before. VR and VL. And I'm going to apply KVL like I did before. So I'm going to have Vs of t is equal to VR of t plus VL of t, which is going to look like R times Im e to the j omega t plus theta I plus L d by dt Im e to the j omega t plus theta I. Made that parentheses too large there. R times Im e to the j omega t plus theta I. So how do I do this derivative? Okay, so what's the derivative with respect to t of the e to the j omega t plus theta I? All right, so to be clear here, I'm going to do this down here so that I don't wind up erasing something. Im is a constant, so we could take that out. So we are taking the derivative with respect to t of e to the j omega t plus theta I, right? I would argue that this is the same as taking the derivative of e to the j omega t multiplied by e to the j theta I. The right-hand term is a constant. So what's the derivative of e to the j omega t? J omega e to the j omega t, right? So this is going to be j omega L Im e to the j omega t plus theta I. Erase all this crap down here real quick. All right. I'm going to substitute in my voltage form now. Right. Vm e to the j omega t is equal to R plus j omega L times Im e to the j omega t plus theta I. And from this, I can say that Im e to the j omega t plus theta I is equal to Vm e to the j omega t over r plus omega L. I have a complex number on the left-hand side. I have a complex number on the right-hand side. We could do a lot more algebra here, but I don't want to waste you guys' time and we're actually running out of time here. We have enough information that we can plug this crap into our calculator and figure out what I is, right? Another way to look at this, let's leave it like that. So how would I input Vm e to the j omega t into my calculator? What's our magnitude? Which is 8 volts, right? What's our phase angle? R was 10. What's omega times L? I would like for you guys to type that into your calculator and tell me what result you get in polar form. $3099, so 310. Do me a solid and scroll up and verify if those are the exact same results that we got for the magnitude and phase angle of the current in the way that took us 35 minutes. Yes. So we can analyze circuits using a complex number representation of our sinusoids and get the same result utilizing a terrifyingly smaller amount of math, okay? Like this method is much, much more efficient. And so that's what we are going to spend the next several class meetings going over. We are going to work our problems in what's called the frequency domain instead of the time domain, where in the frequency domain, we represent our sinusoidal signals using complex numbers, okay? So I'd like to talk to you briefly about why this works in particular, and then we'll wrap up for the day because we only have 20 minutes left of class anyway. So let's say that we have a linear black box network. And I excite this system with a voltage Vs of t and measure a response that is I of t. So we found that if Vs of t was of the form Vm cosine omega t plus theta v, our response I of t was of the form Im cosine omega t plus theta I. It took us a rather long time to do this in the time domain, but we accomplished it. Now let's say that I take that same black box network and I apply slightly different input signal. So let's say that in the second time, I put in an input signal that is Vm sine omega t plus theta v. What should we expect our response to be? Yeah, absolutely. I am sine omega t plus theta I. So if I put in a sinusoid, or if I put in a sine function, I get out, excuse me, if I put in a cosine function, I get out a cosine function. If I put in a sine function, it stands to reason that I should get out a sine function. And that should intuitively make sense because, as we've already discussed, cosine functions and sine functions are the exact same thing, just shifted, right? Well, do any of you guys remember what the homogeneity or scaling property of linearity is? Talked about it probably 6 weeks ago at this point, so not entirely surprising that nobody remembers. The scaling property of linearity says that if we scale the input by a certain amount, the output scales by that exact same amount, right? So if we had a DC circuit and we had analyzed it using 4 volts, and then we decided to change the voltage to 8 volts, whatever initial result we got, we would simply multiply by a factor of 2 to get the same thing. Well, I'm going to scale my input here by a factor of j, our imaginary operator, which means I should observe that my output is scaled by that exact same thing. J doesn't vary with time or anything like that, so it shouldn't mess with the behavior of my linear black box network. So if we take our linear black box network a third time, and I'm not going to bother drawing this, but let's say that we applied a voltage Vs of t that was Vm cosine omega t plus theta v plus j Vm sine omega t plus theta v. Our output, just using the additivity property of linearity, should be Im cosine omega t plus theta I plus j Im sine omega t plus theta I. Right? So we're just adding our 2 different input signals together and then adding our 2 responses together because this is a linear network by definition. Well, our input signal is, using Euler's identity, Vm e to the j omega t plus theta v. What's really, really interesting about this, though, is that the real part of our input corresponds to the real part of our output. So what this means is that we can analyze a circuit using a complex number to represent our real time domain input signal, get a complex output to our system, and know that the real output is just the real part of our complex representation. So if we put imaginary in, we get imaginary out, but looking at only the real part of our imaginary output gives us the exact same result as if we had suffered through 35 minutes of trig every time, just using simple algebraic techniques. Okay. So what we're going to do on Wednesday is dig more into this concept of frequency domain circuit analysis and kind of establish some rules for converting from the time domain into the frequency domain, and then talk about how we can apply all of the circuit analysis knowledge that we currently have to analyzing circuits with complex numbers. So that is enough out of me for today. There's only literally 10 minutes left of class, so I don't even think it's worth really getting started on the in-class assignment. So I say we all head on out of here.